So let's move on to solubility rules and aqueous reactions. So first out, can you please print off the solubility chart that's provided? So the way you use the solubility chart, most solubility charts, not just this one, is you look for the ion that's in the compound that you're looking at. So say for example I'm looking at lead sulfate. So we can either look at lead or sulfate. Sometimes only one of them will be available in the chart, but sometimes both. So let's say I'm looking at lead 2, so lead with a 2+ charge. So you look at lead, and then in the column right beside it or underneath it, it'll give you all the possible solubilities for all the possible compounds. So if I'm looking at lead sulfate, it'll say lead all insoluble except for such and such and such and such and such. You'll see that lead sulfate is actually insoluble. So over here we have a reaction. You'll remember that it's a double displacement reaction. If it's an aqueous reaction and it's a double displacement reaction, one thing to note is if both products are soluble in the end, then no actual reaction happened. And we'll get into that in a second. So there are 3 different types of ways of writing a reaction that's in an aqueous solution. So the first is just the plain old chemical equation, which we know of. So over here I have the reaction between silver nitrate and sodium chloride to make sodium nitrate and silver chloride. So notice how everything is aqueous except for the silver chloride, it's solid, which means this reaction actually happens. Otherwise, if both of these were aqueous, then I would just erase it and write no reaction. So the ionic equation just takes the original chemical equation and breaks it down into the ions. So because this is aqueous, in solution it breaks down into ions. So I've broken it down into ions over here. Same with this. Sodium nitrate also breaks down, so I can write it like that. But silver chloride does not break down, so I have to leave it as AgCl solid. I can't break it down. This brings us to the net ionic equation. The net ionic equation right here just crosses out the ions that appear on both sides of the equation. So that just gives us with Ag plus Cl minus to make silver chloride, which is a solid. Nitrate and sodium are called spectator ions. They're called spectator ions because they're just watching, they're just spectators. They're not really taking part in any reaction. They're there in ionic form before the reaction, and they're there in ionic form after the reaction. So they're not really doing anything. So we just cross them out to get the net ionic equation. So this is the reason why before when I said if both of the products are soluble, then we have no reaction, because it's just all spectator ions. The ions were there before and the ions were there after, so no real reaction happened. So let's do an example with stoichiometry in an aqueous reaction. So if we have 8.7 grams of sodium sulfide and we add it to 350 milliliters of 0.25 moles per liter of lead 2 nitrate, we need to calculate the mass of the precipitate that forms. So over here we have the sodium sulfide adding lead 2 nitrate to make lead 2 sulfide and sodium nitrate. So first thing we need to do is write out the reaction, I did over there, and balance it. So it's 1, 1, 1, 2. Perfectly balanced. The next thing is we need to figure out what's insoluble. So I used my solubility chart and I figured out that sodium sulfide was indeed soluble, so we write it as aqueous. I told you it was a solution of lead nitrate, so it must be soluble. And when I looked up lead 2 sulfide, I found that it was insoluble, so it's a solid, and sodium nitrate is aqueous. So the next thing we need to do is figure out what's our limiting reagent. Remember that from Unit 5? So we need to assume first that sodium sulfide is the limiting reagent. So we need to get the moles, and when we get the moles, it's just mass over molar mass. When we get the moles, we have 0.1122 moles of sodium sulfide. So because it's a 1-to-1 ratio between sodium sulfide and lead 2 sulfide, we must also get 0.1122 moles of lead 2 sulfide. So now we need to figure out the moles of lead 2 nitrate to figure out, if this is the limiting reagent, how many moles of lead 2 sulfide we would get. So we're not given the mass in this case, but we are given the concentration and the volume, because it's a solution. So we can find the moles from C equals N over V. So I've rearranged it here to N equals C times V, which gives us, if we work it out, we have 0.0875 moles of lead 2 nitrate. So also because it's a 1-to-1 ratio between lead 2 nitrate and lead 2 sulfide, we should get 0.0875 moles of lead 2 sulfide. Because this using this equation with lead 2 nitrate gives us less lead 2 sulfide than if we had assumed that sodium sulfide was the limiting reagent. Lead 2 nitrate must actually be the limiting reagent. So we'll use this number for moles in the rest of our calculations. So now to figure out the mass of something, all you have to do is multiply the moles by the molar mass. So to get the mass of lead 2 sulfide that forms, we just need to multiply the moles by its molar mass. And we get 20.9 grams of lead 2 sulfide forming.